This backpack represents the core parameters of the knapsack problem. We have a strict maximum capacity of exactly 4 kilograms and 3 specific targets: 4 kilograms of gold worth $1, a 5 kilogram statue worth $2, and a 1 kilogram diamond worth $3. The 01 in the name defines our primary constraint. You cannot chop the gold in half to maximize your weight utility. You either completely include an item or entirely exclude it. To find the absolute maximum value we can carry, we can build a baseline recursive algorithm. For every single item in the list, the program makes a binary choice: branch left to include the item or branch right to skip it. This tree doubles in size with every new item added to the list, creating a time complexity of big O of 2 to the power of n, while keeping a space complexity of big O of n. Brute forcing every possible combination guarantees we find the maximum value. However, that exponential time complexity means the processing time explodes as the item list grows, making recursion practically useless for large datasets. We have to optimize. This 2D grid matrix maps items against weight capacity. By storing subproblem results here, using tabulation, we trade computation time for memory. But look closely. To calculate the active cell's maximum value, the formula only references the immediate row directly above it. Higher rows waste memory. We collapse the 2D matrix into a single 1D array filled with zeros. Moving across the row, the formula calculates the maximum between keeping the current value or adding the item's value at the current index minus its weight. By abandoning historical 2D rows, we shrink our memory footprint down to big O of W, the weight limit, while maintaining our optimized processing speed. Watch what happens iterating left to right. We process our 1 kilogram diamond at index 1. Moving to index 2, the formula looks back at index 1 for available space. Because index 1 was just updated, it incorrectly adds the diamond a second time. We only have 1 diamond. How do we traverse a single array to ensure data from the previous state isn't overwritten before we need it? The inner loop must run in reverse, starting at the maximum capacity W and traversing backward down to the item's weight. Calculation arrows only point left. These smaller, leftward capacities haven't been updated yet, guaranteeing we reference strictly uncontaminated data. Reverse traversal is the mathematical mechanism preventing unbounded item usage. It is the exact step enforcing the strict 0-1 rule inside a 1D space. Here is that exact logic translated into code. We start by initializing our 1D DP array, multiplying 0 by W plus 1 to cover capacities from 0 to our max weight. Next, we build our 2 loops. The outer loop iterates forward through each item. Inside that, our critical inner loop starts at W and stops just before the item's weight, stepping backward to execute the reverse traversal. Inside that inner loop sits our single update line. The array overwrites itself at index J only if picking the current item yields a higher value than keeping the existing state. This table compares the resource efficiency of our progression. We eliminated the exponential time of the naive approach, then stripped away the heavy n times W memory footprint of the 2D matrix, arriving at a highly efficient O of W space complexity. To solve a space-optimized knapsack problem, follow 3 strict rules. The 0-1 constraint means pick all or none. Space optimization demands a single array sized to W plus 1, and you must always traverse that array backwards. Understanding the difference between a 2D matrix and a 1D array reveals how an algorithm manages its memory under the hood. Mastering that architecture is what transforms a functioning script into a truly optimal solution.